All right, so good day, everyone, and welcome to the second lecture of 124-104 Physics 1A. So yesterday we started our semester by looking at some, mathematical skills that we will use in this course. This second lecture is essentially like the formal start of the physics concepts. So here we will start with kinematics. When we say kinematics, it's that branch or aspect of mechanics that talks about how an object moves. So in today's lecture, we will learn about different terms like distance, displacement, speed, velocity, and acceleration. And we will be defining each of these terms, right? As well as distinguishing between them. We will then move on to looking at how we can describe the object's movement through motion graphs. And related to that is how we describe the object's movements using kinematic equations. With kinematic equations, we're more concerned about trying to determine what the distance, displacement, speed, velocity, or acceleration of the object is. Right, so this lecture is all about a moving object, say a car that goes from point A to point B. Right, we will describe its motion using these terms here, as I've mentioned in the previous slide. So let's start with distance and displacement, yeah? Right, when we say distance, it's essentially how far an object has traveled. Displacement, on the other hand, is how far an object is from the starting point. Okay, the definitions are seem to be similar, but they are actually very different. So for distance, it's how far an object is, meaning you measure the distance along the actual path that the object has taken in moving from point A to point B. And the direction does not matter. It doesn't matter whether the object does a loop-the-loop or does some detours. You measure the actual path for which the object traveled along. Okay. On the other hand, because the direction does not matter with distance, we call distance a scalar quantity. On the other hand, for the displacement, we're only concerned about how far the object is from the starting point. The other main difference of displacement is that the direction for which the object moved is important, and therefore displacement is called a vector quantity, right? So scalar, we don't care about direction. Vector, we care about direction. And as we go along this course, we will talk more about vectors. But for now, we will just define a vector quantity as something that requires a direction, and a scalar quantity as something that does not require direction. We're measuring how far, the dimension how far for both distance and displacement, and therefore they have the same unit. They're both measured in meters. Okay? And this probably illustrates the difference between distance and displacement. Say you have Bart Simpson, who travels from Sylvia Park to Britomart. Okay? When you want to measure Bart's distance of travel, okay, what you need to do is to measure along the actual path that Bart has taken in going from Sylvia Park to Britomart. Okay? Say, for example, you measured 16.9 kilometers as the length of the actual path that Bart has traveled. On the other hand, displacement, you're only concerned about the starting point and the end point during the motion, right? So starting point is Sylvia Park. We use the subscript I, or in some textbooks, they use the subscript 1 to indicate the initial position. And we are also only concerned about the final position. We'll use the subscript F to indicate the final position. In some notations, you'll see the subscript 2 being used to indicate the final position. The displacement is then just the straight line distance between the final position and the initial position. Right? And so it's easy to see that the displacement of Bart Simpson is less than, right, the distance that he traveled going from Sylvia Park to Britomart. So that's the fundamental difference between distance and displacement. Okay, so some more notes on displacement, right? For displacement, we use this notation delta x, delta being, of course, delta, the Greek symbol delta means change, okay? Right? So displacement is change in position, delta x, and you're only concerned about the final position minus the initial position, right? Delta x needs, or displacement needs, a direction, so it can either be positive, negative, or zero. Okay? The direction for positive and negative, they're just sign conventions, so you can choose any direction to be positive and any direction to be negative. But for consistency in this course, we will use this sign convention. If the object moved to the right or to the positive x-axis or to the east, we say that it has a positive displacement. If the object moved upwards or positive y-axis or to the north, we also indicate that as a positive displacement. Okay, of course, opposite directions to that, like left, negative x, or west, downwards, negative y, or south, will give us negative displacements, right? So that will be, this will be the sign conventions that we will consistently use in this course. Right, so say, for example, you have an object that started from this initial position x1 or xi, 10 meters, and moved to the right to the final position x2, 30 meters. What will be the object's displacement in this first example? Right? So displacement, we're only concerned about the final and initial positions. In this case, it will be 30, take away 10. In final, take away the initial position. That's 20 meters. The positive sign that you get indicates a positive direction. As you can see in the arrow here, the object moved to the right. So the positive sign you get in doing the calculation will indicate that your object moved to the right. Right? On the other hand, for this example here, you have a person that who jogs to the left, starting from 30 meters and ending at 10 meters. You want to find the displacement of this person, right? You only need the final position and the initial position of the person. It doesn't matter whether the person made detours along the way, right? You're only concerned about the final position, which is 10. Take away the initial position, 30, you'll get negative 20 meters. The negative that comes from your calculation will give you the direction. All right, negative says to the left or negative x-axis, which is also clearly indicated by the direction of this arrow here, right? So you can give directions in multiple ways. Either you give the sign, negative or positive, or you give the actual word right, left, east, west, up, down. Okay. And of course, looking at these examples and following through, if the object returns to its original position, meaning the final position is equal to the initial position, then it follows that the displacement is 0, but the distance is not 0, because the distance will be whatever length the object traveled through, even if it returned to its original position. All right. Okay, any questions about distance versus displacement? Right. So feel free to pop any questions in the chat box or just unmute yourselves and ask as we go along the lecture. But if there are no questions, then try this exercise. I'll give you a couple of minutes to at least read the question and try and figure out the total displacement and the total distance traveled by the object that starts from point A. So point A is the starting point, and the line, the purple or blue line here, shows the path the object took in arriving at its final destination at point F. Right? So displacement, you're only concerned about the final position F, which is at 10 meters as shown on the y-axis scale. Y-axis scale is measured in meters. So 10 meters, take away the original position, which is 2 meters, and therefore the displacement is 8 meters. The direction, you have to indicate the direction. The positive sign can be used as the direction. It means upwards. Based on the context, by looking at the context of the motion, the object can move directly upwards from point A to point F. So the positive sign here can mean upwards, right? And for the distance, you then have to calculate the actual path, the length of the actual path that the object took in going from point A to point F, right? So each grid is 2 meters. So you just, point A to point B plus B to C plus C to D plus D to E plus E to F. And that gives you a distance of 29.7 meters. And you don't have to give the direction in this case. Good. All right. So when an object moves, we can describe its motion according to the distance it traveled or its displacement. We can also describe the object's motion in terms of its speed and velocity. And there are two kinds of speeds and velocities: instantaneous and average speed and velocity. So let's look at speed and velocity now. Okay. When we calculate or determine the speed, we need to know some kind of time interval, or when we say time interval, it's essentially the time it took for the object to undergo its motion that we are considering. It's final time minus initial time, but usually we set the initial time to be the 0 time, and hence you will often see, instead of writing delta t, we'll just write t. That means the time it took for the object to undergo the motion that we are considering. Time is, of course, a scalar quantity measured in seconds, right? So average speed, okay, when we say speed, it's determined by the distance traveled by the object. So average speed is defined as distance divided by the time it took for the object to cover that distance. In equation form, this is the equation that represents the average speed. The unit for speed can be obtained by using dimensional analysis. The unit for distance is meter. The unit for time is seconds. Therefore, the unit for speed is meters per second. Okay. Right. And because distance is a scalar quantity, as we've defined earlier, speed is therefore also a scalar quantity. We don't care about direction. We just care how fast an object is moving over a time interval. Okay. Right, so here's an example. This person started from the 0-meter position, walk to the right, for example, and then walk to the left. How do we find the average speeds of this person's motion? It's a direct application of the definition of speed, being distance divided by time. So distance, measure the actual path the person traveled. So it went from 0 to 5 meters and back to 0. So that's 10 meters, but continued another 8 meters to the left. Okay. So overall, the distance is 18 meters. Notice how we did not consider negative signs, but rather we just measured the actual length that the person covered over his motion. Okay, and then for the time, time started when the person started to move and ended at 22 seconds at this position. And hence that gives us the time interval, which allows us to calculate the average speed during the motion. Again, here is an application of the significant figures that we learned yesterday. Right, the distance is 18 meters, two significant figures. The time is 22 seconds, two significant figures, and hence we round our answer to two significant figures. Okay, okay, for velocity, velocity is only different from speed in that the direction is important. Okay, so average velocity is how fast an object is moving with the additional information about direction. Okay. So for us to incorporate the direction, the average velocity is then defined using displacement, because as we learned earlier, displacement requires direction. Okay. And hence, average velocity is represented as the displacement delta x over the time interval. And of course, it's a vector quantity because displacement is a vector quantity and direction is important. Good. All right, so looking back at this same example that we used for the average speed, how is the average velocity of the motion different from the average speed? Okay, so we want to find the average velocity of this person's motion with the same conditions as the average speed example we saw earlier. Okay, the main difference is that instead of finding the distance, we now need to find the displacement. We're only concerned about the initial position and the final position of the person. The person ended at -8 meters. Notice how we are now incorporating the signs, the sign being negative, which gives us information that the person moved to the left, right? And take away the initial position, which is 0 meters. So the displacement is -8 meters. The negative sign gives us the direction, which is to the left. It took the person 22 seconds to go from his initial to the final position, and therefore we can calculate the average velocity, which will give us a negative number again. So looking at the significant figures here, the displacement has one significant figure, time has two significant figures. We learned yesterday that when we round, when we do calculations, we usually use the least number of significant figures, and therefore we round to one significant figure. Okay. Our answer is negative. So that means that the position is to the left. So the person moved to the left with an average velocity of 0.4 meters per second. Right. Good. Right. Any questions about speed versus velocity, average? If there are no questions, let's look at this conceptual example. So Jeffrey Mutai, he's the fastest marathon runner. He can run 2 times around the track and field oval in 40 seconds. Okay? We want to find his average speed and his average velocity. And we assume that, you know, when he runs around the track and field oval, he ends at his starting point. Say this is the starting point. He runs around 2 times and ends up at his original starting point. And note that one round is 400 meters around a standard track and field oval. Right? Okay, so we saw these equations earlier, average speed versus average velocity. Okay, for average speed, we want the actual distance that Jeffrey ran. He ran 2 times around the oval in the time of 40 seconds. Hence, his average speed is 20 meters per second. How about his average velocity? Right, his average velocity has to be 0, right? Because we assume that he started at the starting point, at this point, ran twice around the oval, and then ended at his starting point. Hence, displacement is equal to 0, giving an average velocity of 0. Okay. Right, so these statements just again emphasizes and summarizes the difference between average speed and average velocity as we have been talking about. Right. Okay, now for instantaneous speed and instantaneous velocity, okay, the key word here is instant. Okay, instant. So when we want to find the instantaneous speed and instantaneous velocity, we're looking at the speed and velocity at a specific time, at a single instant of time, right? So you only consider a single time. We don't usually do the calculation like we did for average velocity and average speed, right? For instantaneous speed and instantaneous velocity, it gives us only the speed or how fast the object is moving at a single time. If it's instantaneous velocity, it's how fast and in which direction the object is moving at a single time. Okay? And a very good example of instantaneous speed is, you know, when you're driving your car and the moment you look at your speedometer, that number that you see in your speedometer will give you your instantaneous speed at that particular time when you looked at your speedometer. Right? Of course, for instantaneous velocity, it will be the instantaneous speed, the number that you see in your speedometer, as well as the direction where you're moving at that particular instant of time. Okay? So instantaneous speed and velocity is different from average speed and velocity in that aspect. Okay. Right. Does that make sense? The difference between instantaneous and average. Right. No questions in the chat box, so I would take that as yes, it makes sense. Right. So now that we've defined speed versus velocity, let's now define acceleration. Acceleration happens when velocity changes. The formal definition of acceleration is the rate of change of velocity. Okay? When we say rate, it's how quickly something changes. It's something divided by time, right? So mathematically, the acceleration is change in velocity over the time it took to make the change. Right, change in velocity, means final velocity minus initial velocity. And of course, you have the time interval. Or in equation form, this is the compressed equation form for acceleration. Because we are talking about velocity comes into the definition of acceleration, and we said that that velocity is a vector quantity. Acceleration is therefore a vector quantity as well. Okay? And the units for acceleration are derived. The unit for acceleration is derived from the units that define the acceleration. So unit for velocity is meter per second. Unit for time is seconds. Therefore, the unit for acceleration is meter per second squared. Okay. So if acceleration is how fast velocity changes, or the rate of change of velocity, how do we have acceleration? It's simple. If the velocity changes, then you have acceleration, because acceleration is how quickly velocity changes. A change in velocity means either a change in speeds or a change in direction. So as we've learned, velocity is a vector quantity. So vector contains both, velocity being a vector contains both the speeds and the direction. So if either of them changes, then you have a change in velocity, and therefore you have acceleration. Okay, what does negative acceleration mean? It can mean two things. It's either the object is slowing down, because then if it's slowing down, its speed is decreasing, the speed is changing, and that's usually what we call deceleration. Or you can also have negative acceleration even if your object is speeding up. But if it's moving in the negative direction, that will also give you a negative acceleration. Right? So direction is important, as I mentioned earlier. Okay, let's look at an example for how to determine the acceleration. Okay, a car accelerates from rest. Okay, from rest, meaning the car initially was not moving. So that gives you an initial velocity of 0. And it accelerates to 90 kilometers per hour. Let's put units to the initial velocity, 0 meters per second. And the final velocity is 90 kilometers per hour. It accelerates, or it changes velocity in the time interval of 5 seconds. What is the magnitude of its average acceleration? So magnitude, meaning what's the size? meaning we're just asking you about the number and you don't really need to give the direction. When we say magnitude, we're just concerned about the number. Of course, we know acceleration is a vector quantity. It should have a direction, but we're just after the magnitude or the size of the average acceleration. Right. So acceleration, we defined it as the change in velocity over the time interval. Okay, we can expand that as final velocity minus initial velocity divided by time. We set the initial time to be 0, so we just use the final time, which is t. All right, so to find the acceleration, we need information about the final and initial velocities. The final velocity is given, 90 kilometers per hour. The initial velocity, you can sort of intuit from the question, which is 0 meters per second. Notice how the units are different. You have meters per second, kilometers per hour. Your units need to be consistent. I would suggest converting to base units, meaning convert 90 kilometers per hour, convert that to meters per second, right? You can use the method we learned yesterday about unit conversions, but I will teach you a shortcut. When you're converting kilometers per hour to meters per second, simply divide by 3.6. So 90 kilometers per hour. If you divide that by 3.6, and if you do the method we learned yesterday for unit conversions, it's quite easy to see why it's 3.6, because 1,000 meters equals 1 kilometer and 1 hour equals 3,600 seconds. Okay. Right. But we'll do the shortcut here. 90 divided by 3.6 will give you 25. And so that's the conversion from kilometers per hour to meters per second. The acceleration will then be 25 meters per second for the final velocity minus 0 divided by 5. Let me put units here. And you should get 5 meters per second squared. So yeah, so there should be a correction in the unit of the answer there. The unit for acceleration is meters per second squared. Right? Okay, any questions? Right. Okay, so we've now defined the quantities or variables that we use to describe an object that is moving. Okay? And sometimes during an object's motion, its speed is it's not constant. Sometimes it's changing and you have varying intervals or varying times. So here is just an example of a car trip where the car traveled at different distances at different times, and therefore it will have different speeds and different velocities at different times. Looking at tables and numbers like this, it's quite difficult to interpret what's going on during the motion. And sometimes it's easier to look at graphs. And therefore, we have motion graphs that describe the object's motion. So let's now look at motion graphs. When we say motion graphs, it's either position, the x-axis will always be time, and the y-axis will either be position, velocity, or acceleration. Okay. So this is an example of a motion graph which gives us the position of the object at different times. Okay. Y-axis is position in meters, x-axis is time in seconds. Okay. If you're given a position versus time graph, you are able to get the speed and the velocity of the motion from the slope of the graph. Okay. To see that, slope is defined as the change in the y-axis divided by the change in time. Okay. If we look at the y-axis is position. So that means when we get the slope, we're looking at the change in position. And the x-axis is time. So when we get the change in the x-axis, it's equivalent to getting the change in time or getting the time interval. And hence the slope is calculated as the final minus initial position over the time interval. And we've already defined the change in position to be displacement, and of course, final minus initial time to be the time interval. And that's why if you calculate the slope of a position time graph, that will then give you the velocity. And you can see here that the units that you get when calculating the slope is consistent with the units for velocity that we learned. Okay. So how do we calculate the velocity if, for example, you have a curved position versus time graph, right? Position, in this case, specifically displacement on the y-axis given in kilometers and time on the x-axis given in seconds. Okay? If you're given a curved graph, the same principle applies. The slope of the curved graph is still the average velocity. But in this case, you need to work out, you need to get 2 points in your curved graph. Those 2 points will serve as the end points and the start points of the motion. For example, these 2 points here, that will then allow you to calculate the change in position, which is the displacement between these 2 points, and the time interval delta t. Then you can calculate the slope as the change in the y-axis, which we also call as the rise, right? You're probably more familiar with the terms rise over run from school, which defines the slope, right? So by getting the change in the position over the change in time, that gives you the slope, which is the average velocity. Right? For instantaneous velocity, we just want, we defined instantaneous velocity as the velocity at a particular instant of time. So we just want the velocity at this point in time, at say 42 seconds, right? At a single time, velocity at a single time. So how do we calculate the instantaneous velocity from this motion graph, from this displacement versus time graph? Okay. For any calculation from using motion graphs, you will always calculate the slope. Okay, if given a displacement versus time graph, to get the velocity, you will always calculate the slope. And as you've seen in the previous slides, to find the slope, you'll need 2 points along a straight line. Okay? So what you need to do is to draw a line that's tangent to the curve. So this red line is tangent to the point where you want to determine the instantaneous velocity at. Right? And by using the tangent line, you can determine the rise, the change in position divided by the run or the time interval delta t. So the whole point of drawing this straight tangent line is for you to pick up 2 points along the tangent line that will allow you to calculate the change in position and the time interval. Okay. So of course, if you look at your curved graph, it makes sense that the velocity will be different at various times. Because if you want to find the velocity at this time, then you draw a separate tangent line. Okay? And you see that this line slopes at a different angle compared to this other tangent line. And therefore, that gives you an idea that the velocity, instantaneous velocity should be different at different times if the graph is curved. So for example, for this curved displacement versus time graph, okay, at which point is the velocity, meaning instantaneous velocity, the highest? Is it at point A, B, C, D, or E? So while you're thinking about this question, there's a question in the chat box here which says, why can't we just, I suppose, why can't we just use the specific value at the point and divide? So, so I guess the question is, why can't we just use this specific point here, say 30 meters divided by 40 meters? The reason for that comes from the definition for acceleration. So acceleration is defined as the change in velocity over the time interval. Okay. So if you only have a single value for your velocity, say if your velocity is the same all throughout, then acceleration is equal to 0. Okay? So acceleration is related to the change in velocity rather than a single value of the velocity itself, right? And therefore, it won't work to just get this single velocity value at this single instant of time, because the definition for acceleration requires you to get the change in velocity. And yeah, and as you can imagine, you cannot calculate a single a change in velocity if you only have a single point. And that's why you need to draw a line that's tangent to that point. And that's where you get the change in velocity over time interval. And that's the same case for displacement, right? For velocity, the definition for velocity requires you to find the displacement, or the change in position rather than a single position. And with the same argument, you cannot calculate a change in position by just looking at a single point. And that's why you have to draw a tangent line in order for you to get a change in position that satisfies the definition for velocity being change in position over the time interval. Did that answer your question, Ryan? Okay, good. I hope that answered your question, Ryan, but if not, just feel free to do a follow-up question. Another question, how do you know how long to draw your tangent line? You can draw your tangent line as long or as short as you want. Okay? There's no set limit to how short or how long your tangent line is. A smart choice for the length of the tangent line will be to end up at exact values along your X and Y coordinates, because then that will make it easier for you to pick up a value from your X and Y coordinates. it's a straight line. The tangent line is a straight line. So the slope of a straight line is the same regardless of what point you will use along the straight line. So there's nothing stopping you from, drawing your tangent line so that it ends at that point, and also drawing your tangent line so that it ends at that point, and then you can easily read the values off of the x-axis or the y-axis. Right. Good. So I hope that answers your question about how long to draw the tangent line. There's no set rule. Okay, so going back to this example here, okay, at which point is the velocity the highest? And we're talking about instantaneous velocity, right? Because we're looking at different points in time during the motion of the object. Okay. Right, so using the technique we've just been discussing, the strategy here is to draw tangent lines, okay? Straight lines that are tangent to each of the points where we want to determine the instantaneous velocity. Okay. Right, it's easy to see that for point A, you have a horizontal line, almost a horizontal line. Let's just say it's a horizontal line, which means that the change in position will be 0, because for position A, right, the initial, you can take this as the final position, and you can take that as the initial position. The change in position is therefore equal to 0. Velocity is equal to 0. If you and for each of these tangent lines, the slope will be different. Right. Soon you will realize, if you do the same exercise as you did for point A, soon you will realize that the steeper the slope, okay, so for this point C, that's your final position, that's your initial position. Slope is rise over run. You will soon realize that the steeper the slope, the bigger the instantaneous velocity. So in this case, the instantaneous velocity is largest at point C, where the slope is steepest. Right. So let's just look, it's 12:50. Before we wrap up this lecture session, let's just look at this numerical example that distinguishes between average velocity and instantaneous velocity, right? We want to find the average velocity at this time interval, 0 and 11 seconds. And we want to find the instantaneous velocity at this point, 4 seconds. So the motion graph is this blue line here. Okay. For average velocity, let me see. Yeah, average velocity, we need to find the displacement, okay, the rise, the change in position. Yeah, we're looking at this time 11 and 0 seconds. So the change in position will be from 0 to 9 seconds. Remember, your y-axis is position x. So at 11 seconds, your the object's position is at 9 meters. At 0 seconds, the object's position is at 0 meters. And therefore, the displacement over the time interval 0 to 11 seconds is 9. Okay. And the time interval is, of course, 11 because you're looking at the time between 0 to 11 seconds. That gives you an average velocity of 0.81 meters per second. For instantaneous velocity at 4 seconds, okay, the graph, the motion graph is curved. You can see from this blue line here. Therefore, you need to draw a tangent line. Okay, and here you can see the demonstration. It doesn't matter how long or short your tangent line is, but a smart choice will be to draw it long or short enough so that you have endpoints. You have 2 points that coincides with, somewhere that's easy to read along your X and Y axes. Okay. So by drawing your tangent line this long, I can see here that the final position is at 7 meters. The initial position is at 4 meters. Okay. Giving you a displacement of 3 meters. Right? For the time, sometimes you cannot have it all. For the time, you sort of need to estimate a little bit for the final time. So the final time is somewhere here, 6 point something, minus the initial time, which is 1. Well, it was estimated to be, the final time was estimated to be somewhere at 6.5, and the initial time is at 1 second. Therefore, for the time interval is 5.5 seconds. So this 5.5 seconds came from final time, which is 6.5 minus 1 second. It's probably a not so good estimate, but because as you can see, it's a little bit more than 6.5 seconds for the final time, but you can estimate it, and your answer will be 0.55 meters per second. All right. Any question about the solution for this example? No? All right, if there are no questions, we sort of run out of time. We'll deal with the rest of the lecture slides in our lecture, or we don't have a lecture tomorrow, but on Thursday. And then we'll see how we'll catch up in the next lectures. But this is quite a big lecture today because it sort of puts together everything about kinematics. But I hope that by just trying to go over the concepts slower than usual, rather than me trying to cram everything in the 50 minutes, I hope that, it's better. It's a better strategy rather than cramming everything and talking so fast and looking at things so quickly. But otherwise, the video will be uploaded on stream in the next hour or so after our class. We will continue our lecture on Thursday in the third lecture session. If you have any questions, feel free to stay and ask me. Otherwise, thanks for coming, and I will see you in the next lecture on Thursday.